these, football stadium-sized data research centers. It's kind of a weird thing because we effectively went full circle between like the first computers being gigantic and inaccessible to computers being accessible and everywhere, all the way back to a situation where only a select few people have the resources in order to enable these things again. But what I likely see happening at the end of that process is another turn back toward the idea of either a reduction in complexity as a result of some breakthroughs in the data understanding, or some mechanisms that are entirely different than the way we've been approaching it, right? So a true novel solution could come along to solve some of these problems. Classically, a dynamic system framework deals with just a time set characteristic such that the space occupied at some time t characteristic, right? So this would be the current moment. We could look back at context based upon what was happening before we effectively started evaluating, right? And then we could follow that context forward as a series of time steps. Each time step contains a full set of context relative to the current feature vectors in the space. So you can think of these as frames of a video or words in a sentence or pages in a book, etc. Each individual one is a single sort of discretized thing that is moving along in series. And a key characteristic that's involved here is the assumption of dependency or determinacy. That means that at some time t, the values from some time t minus 1 were inherited from it. So we know what the current status is, right? And maybe we had within a standard recurrent framework the capacity in order to pass that frame information back into the network such that time t minus 1 was still available at some time t. Now, a classical system is effectively drawn up for a standard frame calculation such that we utilize a hidden time sequence series set along the input vector alongside of the change or transference within the primary functional approximation, right? So we treat the whole network as a state-driven system, and we describe the state-driven system with respect to this idea of H as a hidden time state. So a hidden time state, the whole network is being utilized to process the data, but a component of the hidden network is actually a piece that feeds back to itself. So, have you guys ever worked with one of those pumps that you had to pump by hand out of the ground to get water, right? You know that sometimes you have to pour a little water in them to get them to work to begin with, okay? That's what I like to say here is we're priming the pump of the system. We're going to have one time step in which there is no functional context that's going to be necessary for us to then take that context and pass it back around. So the first time sample of the system will not have an understanding of existing context. So what we actually have is a single sample inference initially, right? But then the second sample at the next time step, the system is going to take in the new data, but the previous sample data is going to be present in order to give context to the new data. This is what we consider or refer to as classic recurrent networks. We dealt with these or talked about these earlier on. The more structural elements in play, right, the deeper the system goes, recurrent systems have additional side memory characteristics and state memory characteristics that allow us to be able to feed in operational memory that we can utilize in that context space. So notice here we have the actual hidden element playing into some op state, right, characteristic, and some latent representation with respect to some additional external state space response. We pass off of the information from that side memory characteristic, right, relative to the pass off latency. The output at each sample H becomes an input for each of the sample H hierarchies in the next sequence, as well as the notion that those states L, loss metric characteristic, right? That's the latent understanding of what we're actually getting out of it, okay? So how do we create a loss function to categorize here? We're going to take what we're inferencing at the moment from what we know in a ground truth state exists at that moment. What should happen as this network matures along time? Typically, we think about the network maturing along epochs, right? So in a standard feed-forward network, we treat an epoch like a isolated time step. But instead, what we've done now is we've fed some of the output layer characteristics back into some of the previous layers in the system, such that when the next sample comes in, some of what was processed or recognized, some of the features that were extracted from the previous sample become part of the inputs for the next time set sample. This interesting aspect of it is if we keep the right pieces of information, we're actually going to keep improving the performance of this system such that it is effectively going to converge over time. So if we have effectively a video of a person standing there, right? And we keep treating and handing back these elements of the vector of the person through the system, what's going to happen? Our confidence that this is the person and this is where they're located in space, even if maybe they're moving around a small amount, should still continue to increase because we're learning not only from the process of the network maturing, but from the process of what information from previous outputs we're able to take in. So in effect, we're learning from past mistakes because we're taking in some of our output. That's a really interesting aspect. If you know what you guessed last time, it actually refines what you should ask the next time. Think about how we take quizzes right on Canvas. You give the answer, right, and then the thing comes back and tells you what answer you guessed. Let's say that it doesn't tell you what the right answer was, but it did tell you what the wrong answer was. Okay, what have we done? Crossed off one of those answers in our head, and now our past experience can do what? Refine our future experience such that we further get a better job when we run a secondary attempt. So even though we don't necessarily know perfectly what the right and wrong answer is here, this isn't sort of a bubble sheet style test, it is a loss metric reduction process that can be as simple as the correct categorical classification of an object. It could be something like the spatial decomposition, right, the segmentation mechanisms. So the recurrent mechanisms are actually common within those spatial segmentation models because they refine their understanding of that particular image by pushing it through the system several times in order to narrow in on the actual spatial characteristics of the segmented item. I know we've talked about this to a certain degree, but I've already described this process by which we take the output and convey the space. I don't think we talked about bidirectional networks, though. Bidirectional networks are where we may have talked about these very early on, and I want to highlight them a little bit more now that we have some kind of internal knowledge of the system. Once again, we have what? Feeding forward with respect to the hidden layer characteristics. But we also have something else that's playing in here where we have this G system that's playing in effective reverse. They are actually two of the functionally the same process, right? They're the same concept, same item. They are a hidden network. One is playing the sample forward and the other is playing the sample backwards, all right? Here's the relationship. Natural language processing probably benefits most from bidirectional memory systems or recurrent networks, all right? There are bidirectional RNNs and there are bidirectional LSTMs. We're going to talk about LSTMs today. That's long-term, short-term memory systems. I'm going to attempt to describe to you something that I find relatively complex that I spend an inordinate amount of time on in my own dissertation work, but I think is a really kind of a revolutionary concept in some senses because it models so much of the way our mental processes work, right? We did a lot of introspection and we realized we were kind of missing some pieces of how we make sense of temporal processes. But by playing one system forward and the other system backwards, and by treating the relative our input of the system with respect to the forward process as the input for the reverse process, you're actually able to see both forward and backwards in time, right? Each frame gains full context with respect to the thing that came before it, what the situation was leading up to it, and what happened afterwards. Because sometimes we're going to have to do some deductive reasoning, right? Figure out what happened here, right? And then sometimes we're going to have to do some inductive forward processing. We're going to have to kind of theorize on what's likely to happen under the circumstances. So the quality of classification, the quality of segmentation, probably these are the two primary tasks, but another one is one that we haven't talked about a lot, and that is things like signal-driven metrics, okay? Bidirectional recurrent networks were some of the first systems that were employed for taking audio and attempting to decompose spoken speech into contextual word embeddings. So any of you guys who have taken NLP or studied NLP or studied signal processing will understand that when you look at the waveform of a singular word, you don't learn everything about what that word contains. You don't learn everything about how to classify it or how to contextualize it in order, right? It doesn't all come out perfectly in order. Sometimes you're going to have to look back at what's happening previously in the signal in order to be able to tell where the inflections are changing with respect to that audio characteristic. So some letters change with respect to the letters that are before them, right? Some letters modify the letters that are after them. So when it comes to spoken forms, we have this notion of trying to decompose what that sound, that waveform that's been turned into a signal looks like. So we're going to take time steps of it, and we're going to sort of look forward and look back at it, place it in the scope of our understanding and say, oh, well, this looks like it belongs to this looks like it belongs to this. What's going to happen as we go through the sequence? Having the context of what came before, having the understanding of what comes after, is going to increase our confidence in each of the phonemes, the sounds that we make when we speak, being identified in order in that sentence. Right? They affect each other, they modify each other. What's going to happen to the classification output of the system, the quality of the classification output of the system as it goes forward in that state? As it goes further into the word, what happens? It's going to get better and better at being able to tell what it is. Right? There's a reason why it's probably not good typically to interrupt somebody while they're talking, because you don't know how their sentence ends. Okay? You're going to run forward in your head, you're going to extrapolate that sentence, but they could say something at the end that could clarify something for you if you had it to relate back to in context. This is the interesting part of the way our brains work, is the moment we get it, we start sort of running it over, recurrence in our head, right? And then as soon as we start processing that data, we're also getting it in line with the new information that's coming in, right? So we have an active memory that's running, and then a new working memory. Those two things reside in the same space, and they're effectively running in cycle with one another so that it can refer forward and backwards in the space. This is also useful for the idea of thinking about just word embeddings with regard to a sentence. So if we're going to do natural language processing, something like constructing a sentence or deconstructing a sentence for sentiment analysis. Does anybody know what sentiment analysis is? Not know. Let me say not know. You don't know what anybody not know what sentiment analysis? Okay, I'll tell you. Sentiment analysis is, what do you mean by what you said? Okay? So I'll give you the example of a famous sentiment analysis data set. That is the Internet Movie Database, IMDb, comments section.
Oh boy.
Right? See? Okay. It's a famous data set. If you want to mess with it, it's literally one of the ones you start with, right? Why? Because typically what do we have at the end of it? We have a thumbs up or a thumbs down, right? That's an additional vector piece that we're actually able to utilize as a label, right? Such that if we look at what they said and we go, okay, this should be positive because they gave it a thumbs up, right? Only rarely are you going to have the person that be like, it sucks, you know? But I mean, that's a situation where that's out of scope, right? That's out of sequence. It doesn't make sense. It is against what we would see as being normal, so it's out of distribution. Most people are going to use certain words. Many of those words have both denotation, right? That is their direct dictionary definition as regard to their semantic ordered analysis, right? So when we think about the parser that is our brain that reads words, we're going to think about it following them in a sequence and constructing a concept out of effectively the programming language, which is where we write sentences, okay? Because I'm programming your brain when I speak a sentence, technically. That's kind of the way in which the programming language works. But you're putting it together, you have an assembler in your brain that's putting those words together in order to construct it and attach it to higher level items. So sentiment analysis is a way in which we can say what words have a connotation, all right? That's effectively not the dictionary definition, but maybe a word that could be considered not the best under the circumstances or in reference. So sometimes people can be creative in the way they use words, right? Or maybe use a word slightly different than it might be in its strict first dictionary definition, right? Words have like 3 to 10 definitions, okay? We have to figure out which one we're talking about when we're using that particular sentence. I'll give you 2 sentences, right? The bat hit the ball versus the bat flew in the cave. Notice, bat means something different in each of those 2 sentences. If I have the ability to look back and see if there's some information about what I'm talking about, right? And refer to something that came afterwards, right? Bat and ball, right? What if I say the cave was full of bats? This doesn't change the meaning, right, of what bat means in the sentence, but now instead of bat being a modifier for cave, right, cave is present first and then bat comes afterwards. So I actually have to be able to look both forward and back in order to develop the relevant context of that word. If I have another word that within the context of something else can sort of be seen to have negative feelings, we say it's sentiment, right? Sentimentality is one of the word that root comes from, right? So I'm sentimental, that means I hold on to good memories, I like to think about feelings, I like to have old pictures of family, right? It's emotional, it triggers an emotion. Why am I talking about triggering emotion with machine learning, okay? Because the goal of all this stuff, what is the goal of all this stuff in the end? We wanted to figure out how to make something that's like us. Yep. AI ultimately is a reflection of humanity trying to replicate ourselves in silica in some respects. So the idea of having to have contextually driven systems where time matters because we are a technically 4-dimensional construct, or I say we're a 3-dimensional construct in a 4-dimensional space-time, right? We're moving through time. So we have a different set of perceptions than even something that is getting 3-dimensional data and trying to make sense of it as all happening at once. So think about it this way. If you put in a video, right, as a tensor and fed that tensor in as a sample to the system, we know how we could process it, right? You could run convolutions on that even with 3D kernels, and you could get something of value out of it, right? But what would be the problem with that? It would be seen as all happening at once, effectively, right? The whole thing happens as if it is a volume of data taken at a snapshot characteristic. We're going to have to treat it as things that are happening in individual packets. We're going to have to treat each individual packet as its own sort of structure. We're going to have to utilize some information about that as we go forward in the system. One of the problems with depth and recurrence in a system process is there can be some instability depending on how far back we're going to want to try to hand these off. So ResNet is a recurrent network. I would not suggest unfreezing the weights in ResNet and trying to train it. Okay? There's some reasons why. Primarily because of the fact that it gets huge when it goes from running as a forward deterministic model to having all of the side memory it has to have in order to store the previous states at some module down the line that feeds back into some module in the previous up layer, right? So now we have things that are passing off values, holding them, storing them up, doing all of this processing characteristics, and we're attempting to now adjust the weights of those things such that we're seeing how much of it we're actually sending back. Now think about that portion of it. The output of a relative element in the system, right, sent back to some previous piece of the system would have a relationship of dealing with processing of that system as well, okay? We've been talking primarily about temporal spaces, but let's talk about how things, or let's think about how things are processed with regard to depth in a system. We saw the UNet structure in which we passed it off to a more and more pooled representation, such that we could have improved multi-scale performance for the segmentation. This is effectively the idea that I'm going to pass off features that I have found, or recombinations of features at a higher level of abstraction, and I'm going to send them back so that the system can have context of what it's looking at now based upon what I found when I reduced the scale quality, whenever I put in the right detection framework into that particular processing sequence. So knowing how much of what to send back is a factor, right? Do you send it all back? Does it all become part of the input? Or does some of it just become part of the input just to give you a general idea of what's going on? Not to overweight your impression of what's happening, but in order to give it some context to what it's seeing in the general scope. Do I send the entire array? Do I send only segments of it? Can I drop out segments of it so that it doesn't have full reciprocal context? All of these things are possible, right? And they're all things that people are trying to see what they can do with regard to the increased functionality of recurrence. So we have previous hidden state operations that take inputs from future hidden states. So as the network gets closer to the output side, those layers, those convolution layers, feed back in as inputs, right, that have their own weight characteristics of how that current node and that array of nodes actually take in and process that information. So we can adjust those as well, but the methodology for doing so is very different than what we've dealt with beforehand, because how do you adjust the weights for something that happens later in the system, right, relative to earlier in the system, and the output of that process is actually deterministic on its own input. Wait, hold on. Everything's going crazy, right? It's like I'm the snake eating its own tail. So the reason why we say that we're going to sort of gate the recurrent process, and why we need to talk about this later on, is because those systems can't be resolved entirely with just this spatial understanding of recurrent frameworks. So LSTMs, they stand for long-term, short-term memories. Now, there were long-term memory RNNs, and those were things that had multiple connections. That was effectively where each layer kept feeding back to the input layer, okay? So it ended up with a big set of context that was all at the very beginning of the system again, right? Looking forward at all of the features that the system would find. What do we think about that? That's a lot of extra work, right? That's a lot of weird, self-informative context that could give you some bad impressions in some way. What do we also don't want to deal with on that, right? We don't want to do the math. We don't want to do the programming that has to explain how we pass off that data back to the previous layers. Also, they didn't perform particularly well. But there was this particularly interesting idea back in, I think, honestly, this started back in the 90s in concept, but probably became actually feasible in the early 2000s in implementation, right? Some things were actually thought of before they could really be built. Neural networks, for example, I think we talked about this early in the class. 1956, Fukushima wrote the first paper, and by the end of 57, they had built a model of it that was working, an analog version of it that was working at a Navy research base, right? So we've been doing this a long time, but there was a big period between 1957 and when we started to really see these things coming into their own in the 90s, when we got computers that could actually do the volume of calculation that was necessary in order to backprop the gradients in the system. So So what am I actually looking at here? This is a single cell of the cell-based LSTM model. So this whole cell represents the actual structure at any given time step, okay? All of this exists, and all of this exists in sort of a discrete time framework, such that each time step is going to have a relationship between these components that are passing off information to the next instance of this particular network at that time, right? So it's an entity traveling through time, right? We've instanced the AI. We've instanced the LSTM, okay? It is existing. And it is going to have not just context about its own processed information, it's going to have context about what was there, as well as what decisions it made based upon it, and here's the other portion. It's going to be able to decide to be able to forget things. This is the one interesting portion of it. It's not everything that you see and not everything that you track relative to time in a network, right, is important. Not everything do I need to pass back or pass forward or keep sequentially active in a system. Now LSTMs, default LSTMs are just feed-forward systems, right? They can be modeled by a simple, relatively simple structure where we see a feed-forward process across the standard time space, right? But we also have a secondary gated input, we have a forget gate, and then we have an output gate operation. Notice all of these are hooked up to something. All of these are hooked up to something. Previously, what have we done? We've just had a feature vector coming into our network characteristics. But notice, there isn't a lot of network here to be had. There's not a lot of connectivity. There's not a lot of weights internally to optimize based upon. But there are some weights. These connectivities have weighted components involved with them, and they can adjust. But we see a couple of things that are happening here, that there is a input relationship, that's the core data that's coming into the system. I then have some state value operation X. That state value is being passed into an integrator module, all right? It's just adding together the values of that state network. Now I can have some belief information, effectively that's saying what I think I know about what's present, and that's the information I'm retaining, okay? I have both a long-term memory, just like a human, right? I have context based upon the whole of everything that I've processed, as well as some short-term memory that I can have as just workspace, right? I contextualize these based upon the difference between a filing cabinet and the desk, right? You can have a file on your desk, but you can't have all the files on your desk at once or else it gets too cluttered to work with. So the short-term memory must, by obligation, be relatively contextual to what you're currently working on. It also has to be relatively small, because if it's not relatively small, then you have things like lookup operations that take entirely too long to contextualize what you're looking at relative to what you're currently seeing. So if you want to match some patterns, right, you're not going to have a whole pattern matching database like we think of as the kernels in a CNN. You're just going to have whatever number of patterns and observations that are relevant to what you're currently seeing in the system. We're actually going to continuously update that, right? Whereas, see, from the perspective, if I'm watching a frame of a video and I see a ball enter the frame of the video, what's going to happen to my vision, my interest? Pop right up there and follow the ball, right? And as soon as the ball starts to track across the space, I'm going to follow it. What happens when the ball leaves the frame? I'm going to forget it. I'm going to forget it. I need to forget it. Why? Because if I keep that file out on my desk, it's just going to become a bigger and bigger pile, right? I need to fold it up. I need to put it in memory, okay? In case I see another ball come along, right? Maybe by 2 or 3 frames along, I might go, wait, I think there was some correlation here to something that I saw previously, and I can compare it to the larger, longer-term memory system that's handled for multi-gate operations.
Just a quick question.
Yes?
They all have sigmoid activation, is that correct? Like for the input and the gate?
Those are just, I think that's just a standard symbol. They're not required to. Matter of fact, some LSTMs do use ReLU, and some of them use leaky ReLU, as well as E-ReLU, which is a adjustable inhibition. All right, so there are some higher level and more complex activations that can be utilized, put into place in LSTM systems. So they can inherit more complex functionality by having more adjustable nonlinearities, right? So why the sigmoid? Primarily because of the fact that we're just looking at the likelihood of needing to keep it versus the likelihood of needing to get rid of it. So since it's a likelihood-based characteristic relatively pushed towards some kind of saturated index, 0 or 1, we say the likelihood of value or likelihood of correlation is related to the likelihood of value with respect to necessity. This is typically how well correlated the next sample is with the previous sample data, right? So if the ball has only moved a little bit, that means that most of the frame information hasn't really changed. So if I was to use this in a spatial operation, this could be abstracted to spatial data as well, right? But typically, we're going to work with it for things like sequence data for learning words and embeddings in the words, such that we're going to say which words do we think do we need to keep track of. We're going to have certain words like high frequency articles, a, the, ands, right, that are not going to have a whole lot of utility. We're going to be able to have that with respect to our long-term memory to be able to know certain characteristics of the linguistic space, right? The linkage to the embeddings, such that we can use probabilistic functions to determine how significant or necessary it is to retain this piece of context such that it can be useful later on, right? So effectively, we're looking at it and saying, I need to hold on to this because I haven't seen this very frequently. And as a result, I need to pass it forward so that I can have some degree of contextual representation for it, okay? That's the superpower that this thing has, is that it can probabilistically attempt to justify the necessity of an item that it might need later, and it can even learn how to determine what pieces are most important. That's the key learning factor, is underneath of the hood, if I need to know what I have to have in my short-term memory, right, and what needs to go in the long-term space, right, in the larger storage apparatus, I can even forget things in the larger storage apparatus. Why would I need to forget them? Because eventually I'm going to end up with such a large set-aside memory. I'm going to be trying to keep track of such a diverse set of information that the lookup times and comparison times and all of the other value assessments that can go on with the internal processing of this system don't produce any value, right? This item is not needed anymore. And we can even look at it, maybe how long into this processing sequence we are. If we haven't used it for a long time, probably safe to get rid of it, right? It's a bit like a garbage cleanup mechanism within a programming language environment. So we have a forget gate that characterizes a new input operation for a state update process, right? We have a self-entrainment loop. That self-entrainment loop keeps track of the current cumulative state operation. And then once the cumulative state operation relative to the input gate forget gate operation happens, the output gate will determine, right, whether or not this particular piece of information is needing to be contextualized, right? Does it have to have some context to go with it? What is being passed to the next state? I take the output and I'm going to come back up here and I'm going to push it back through this input. So these things hook together in a chain. This whole module is present at every point, right? And it feeds back on itself in the sense of the output becomes part of the input. This is as similar to the recurrence operations we had beforehand, but it's not the whole output. Now I'm making decisions on what portions of it I'm keeping and what portions of it I'm not. That's the reason why I mentioned it earlier as to the things that RNNs really don't provide us with a lot of ability to do, because we can't parse which segments of which feature we found later on down the line that we say, oh, I need to know that I found the blades for the ceiling fan, right? In order to know to look for the ceiling fan, or I need to know that I found the seats or for chairs in order to look for a dining set, something like that. if I don't have or I don't have the context characteristics to determine the utility of that information, I can't decide, I can't make a decision about what is and what isn't important to keep. Now, I've mentioned this a couple of times, but I believe that that particular capacity is probably one of the strongest things linked to acquirable intelligence, acquirable information, right? You can learn to be smarter. How do we say you learn to be smarter? You learn to be able to divide the wheat from the chaff, right? The important from the unimportant, the useful from the useless. So LSTM's primary utility is to be able to be smart about where to keep what, okay? And how to contextualize it within the framework. Now, this is the visual representation of it, and I like the let's further clarify and the immensely more complex diagram. Okay, like, hey, let's clarify. You know, it just blew up. Okay, don't get intimidated by it because it's really just the same things we were looking at beforehand. Let's look at the things we have available to work with. We have inputs. We have three types of inputs. We have the input vector characteristic. We have the memory from the previous block characteristic. This is our side memory characteristic, right? This is actually the kind of long-term memory designator. This is the thing we keep track of here. And then we have the output from the previous block, okay? That is effectively our short-term memory. Now, the reason why I say that type C memory, the side memory characteristic, is more or less long-term is because memory from previous block versus output from previous block are different from one another.
That would make sense.
What I have decided is important at previous block may actually contain many previous blocks designation of importance, all right? Everybody so far has gotten the opportunity to make a contribution to that memory space, and as everybody gets a contribution, as every sort of time step gets its own contribution operation, we're going to have some memory that we maintain, and then some contextual representation that we have as well. Outputs of the system, obvious. Memory block from current block, this C of t, right, relative to C of t minus 1. Right? That's really tiny, it's hard to read it, so I'm just going to tell you what it says. So that's C of t minus 1, that's C of t, okay? C of t is over here, C of t minus 1 is over there. That makes sense. These are Legos. They hook together. They've got this one has two little studs on this end, two little studs on that end, and we just chain them together, okay? We make however long of a chain we need in order to be able to process however long the chain of parsable information we're passing to it is. This is also an additional power that these systems have over CNNs is they can process an arbitrary length of information without having to have a different architecture. Sentences vary in length.
Right.
So if we have sentences varying in length, then we need to be able to parse all the sentences with roughly the same structural characteristics. So since the LSTMs can be chained together, depending on how many components are in the sentence, we can make one arbitrarily as long as we want, and it still has the same utility. The output of the final output of current block characteristic will be the output of the full system. However, we're also getting some interesting information here with respect to the current output block being passed off to the side as well. That means that we can look at the current inference characteristic of what's going on in the network by seeing what is being passed between the blocks. We can look off to the side, and off to the side is an array that's constructed that contains the output of each block, right, irrelevant of how that output is passed off to the next block. Because once they're hooked up together, this h of t becomes h of t plus 1 in the next instance version, right? This one feeding off to this one, feeding off to that one. So unless I keep a copy of whatever the output is at each block off to the side, I'm not going to have that context to assess later on because the output becomes the input, right? This is a bit like dropping the activations out of a layer. So in a sense, we can see these as the features extracted by the sequence processing of the LSTM. You can feed that as a vector off into another system. That's a really cool operation because it's going to gain context, and that context is going to shift throughout the sentence and the relationships of that context are able to be processed by another network that may be a feed-forward style network, taking each of the H of T outputs at each time sample step and taking those in as a feature vector characteristic. Now, do we do that frequently in design applications? Not so much, but that's actually part of what's happening with transformers. I'm not going to get into that right now. I'm going to give you guys 2 videos to watch with regard to the transformers, and hopefully that will prime you guys' pump, okay, to get you thinking about how those work together, and I'm going to do my best to describe some of the internal characteristics of it. They're about 20 minutes-ish, I think, maybe a piece, and I think I mentioned them to you before. They're the newest of the 2 chapters 5 and 6 of the discussion from 3 Blue, 1 Brown on transformer type networks, okay? They have a similar relationship to the fact that they have some memory and they have some internal vector characterization, right? They have some data about the current status of a thing. They might have some values being stored about the encoding. And we're going to also be able to keep track of what's happening to them in terms of their output along the way of the system. So we're able to x-ray and see into it and get a sort of videotape time reel of what it was doing as it was making the process happen, right? The other thing that's interesting about it is once we're able to decompose that understanding of the system, we can get into a little bit more precise updating process. We can tell it what it's doing well and what it's not, right? Some of these values for these nonlinear activations, baseline sigmoid operations are going to take just these internal op states for the introductory state update framework, right? So that's giving the initial state assessment, goes through a summer, and this can be whatever dimensionality we want. This can even be an array. It goes through a network and then goes into a summer, and then there's an activation characteristic along with it. That activation characteristic is going to determine whether or not the values stored in the current state characteristics do what? Update that vector x, that latent vector x up at the top that is involved with the memory that it gained from the previous block. Okay? So the memory that it gained from the previous block has now been compared at a relative state activation, has been initiated or initialized to do something with it with respect to the data that it brought forward. Okay? That can mean a couple of different things, because the next element of the system, right, has a relationship of ownership to that data. We have an initial biasing characteristic here, right, so that adjusts the activation for this sigmoid operation. So we can learn some parametrics to be able to adjust the sensitivity of new input relative to how much we're keeping from the previous memory. What happens at the end of this process, right? Down here, let's look at the end. I'm going to take some new information, okay? I'm going to take it, what I learned from the new space. I'm going to run an operation on it, and this one runs a hyperbolic tangent function. Now, why would the hyperbolic tangent function relative to the sigmoid in this space be kind of feel like it has a little more utility at the moment? Some elements are going to be positive. Some elements can actually be negative.
Yeah.
This is interesting because that gate relative to the state operation that's presented there, right, which is present by both the hyperbolic tangent function computed for the input state operation, right, as well as something that we need to look at first. I take the current state, I pass it into this internal state operation, and then I pass that off into this vector, internal vector x. If this internal vector x is going to be added to this vector x, right, which is present from what's passed from the side memory, I take the side memory, I make the comparison to the operation, take the output, take the side memory, pass it off to this priority element, right, the gate operation, and then that goes up and becomes part of the input vector. What happens if this is a negative activation? What is that value x above it going to be? It's going to be a negative value, right? Or a positive value, depending on what the input is. It's going to effectively reverse it if it goes into a negative activation. If it goes positive, what happens? That means it gets added to the memory. If it goes negative, it gets taken away from the memory. So whatever is passed off, that little integration module right there is where the system makes the decision about the operation of what's going to be passed off as the memory from this node in order to become the current memory output block. So the past memory gets set off to first processing the data, secondarily processing the internal competition, right, with the existing data frame space. How useful was what I compared to, what I got out, right? And then the update process in this secondary framework is going to change the value of the memory based upon what it found in this new frame, right? So new discoveries are added to the memory. They can have a variety of different output characteristics. The activation of that output memory comes back through a hyperbolic tangent function. This is an interesting relationship because now some of that memory, some of that what I've decided to keep, is now going to influence what I'm outputting.
Okay.
Do you know what I'm saying?
Yeah.
Do you see what's happening here?
Yeah.
Okay. Input here, passed off through another activation, through another latent space, right? But a hyperbolic tangent function is going to take the side memory, and that memory is going to have the ability to influence that latent space before that latent space becomes the output. Easy. 1,500 simple steps. Okay? Walk through it one more time.
Oh my god.
I'm just going to walk through it, okay? I want you to see it context by context. Because I think this will do better. I wanted to do the opener operation, right? Try to walk through it all. Now I'm going to do it piece at a time. Forget gate characteristic. Compare what comes into the system with respect to the previous output of the previous node with respect to the new updated information that's coming in. Okay? So this is everything from both the output as well as the side memory. This is short-term memory. This is long-term memory, okay? This is current, the value that is attempting to influence the current state. That's the interesting part of it, right? The input is actually trying to tell you something about what's happening, what's new. So that value goes through the activation and goes up and becomes part of the integration process. New memory value, I already talked about this relationship here, passes off existing memory as well as new memory attempting to influence as well as what? It's actually keeping track of the previous input. So x vector, the new x vector at x of t is influenced by h of t minus 1. It's influenced by the output activation of the previous node as well as the new value activation for information coming into the system. This is effectively the same as the recurrence process. But the difference is now we have two activation characteristics involved here, one a hyperbolic tangent and the other sigmoid, right? Determining how important this particular thing is to add it to the new memory operation. The value on the side memory, all right, those control value characteristics are the things that help the system in gated operation, right? We say, does it go through, does it get added to, does it get taken off the stack, okay? Output process says, I know what I had, okay? I know what I had. I know what I have now. I know what I decided that I was going to keep from what I had before that may have come from more than just the immediate block beforehand. Why do we know that? At the beginning, the forget gate tried to decide whether or not the stuff was effectively relevant. Right? I said it's going to take what it's looking at in context what it had been seeing, and then it's going to try to influence that side memory. What the degree to which it influences it could either be to effectively reinforce it and say, hey, yes, I believe that's important. Thank you for bringing that to my attention. Okay? And the other thing says, no, that's not relevant. I want you to kick it off that stack. I want you to adjust it such that that integrator up at the top does what? It actually changes the internal memory value of the module structure, right? Such that this becomes both what is output to the next system, right? And it doesn't necessarily have to do anything with that particular module. This module could, in effect, have no changes or apply no changes to that side memory, right? No new information was collected. Only the information that was already collected was useful to my frame data. This is relevant to that idea of saying if I already have the baseball and I'm tracking the baseball, nothing else has happened into the frame, then why do I need to add anything new, right? I'm not going to take anything away because nothing has been removed that I consider of merit, but I also haven't found anything that's really shaping my perspective on what I'm looking at. This output operation being passed off to the next time state system and feeding in has that interesting influence characteristic of being both applied to the output as well as being applied to the input of the next module system. It gets a little kind of weird weight to it in that sense, right? The side memory has some significance here. The side memory actually influences the output as well as being part of the output. Crazy significant, right? So we're going to have to be very careful about what we keep up there. We have to be very, very careful about it. Because that is a long system context chain that's providing us with what is considered to have maximal significance relative to the future utility of the network. This will matter whenever we get to talking about the next item, okay? Transformers came from a paper called Attention is All You Need. Technically, they're borrowing some of the stuff that's happening in this framework, and that part of that framework is the idea that attention tells me what of what I've seen is important, right? I pay attention to the thing that matters. So my attention can shift, that is where I'm looking, what I'm looking at, what seems to be of significant and elemental value, and I can learn to pay attention to the right things. The LSTMs also do what? Adjust the parametric characteristics, the biases, so that they influence the activation outputs relative to the input system, such that what happens? They are learnable parameters that adjust the degree to which new information is being presented or integrated to the output, as well as new information is being sent to the side memory, right? As well as what information is being removed from the side memory, given the context of the new information. I just worked through the whole thing backwards again, okay? All right, let's talk about something that's interesting. We haven't talked about this one before, but I want to mention it, is advanced networks such as hyperspatial transforms, which this is a hyperspatial transform because it's again across time, right? It's a high dimensionality system, can sometimes run into issues with gradients that can explode, right?
Yep.
Why? Because effectively they get towards a region of the system in which they're keeping integrating positive values. It's a self-reinforcing system. You keep adding to it, you keep adding to it, keep adding to it, right? It just keeps saying, the gradient tells me to just keep increasing the weight here, right? Everything is just telling me that down is that way, okay? What has happened? We have totally lost the thread of what's happening in the system. The system has effectively started to hallucinate a little bit, right? It's not calculating the right things anymore, and it's gotten into a weird space with respect to the gradient calculation that maybe it's sort of stuck in a strange place. Now, ReLU activations actually have this design characteristic where they can cause some of that sort of characteristic to be minimized, right? Because they have roughly the same gradient because they're a continuous slope. But these sigmoid activation functions can get into weird spaces where they sit right on the edge of a gradient characteristic, and as we keep moving it, that actual value doesn't seem to change, and it's in a really high grad space, but the value output for the immediate error is not changing. It's probably because of the fact that there's some error summation value that's not being appropriately counted. But what we notice here is that for a strange error surface operation, where you have a steep value indicator, what's happening there? I came up against a region of the gradient that was effectively like, boom, straight up, effectively, right? So it's this huge gradient offset. What we would actually like it to do is I would like it to come to the edge of it, and I would like it to slowly come down that edge. But what happens whenever we talk about this explosion operation? I'm sitting right up on the top of the sigmoid transform, such that my value is about as sharp as it could possibly get on the edge of it, right? Because it's effectively a straight drop, and I'm getting a massive increase in error performance, right, in a very short interval. This is actually bad because what? If we're making the assessment based upon the instantaneous gradient, that is a huge gradient value, and so what's going to happen to it? It's going to shoot over here, because even with a small learning rate, that huge drop-off point is so big, right, that it's going to explode and push against the other side. We're going to instead limit the possibility of the gradient to be able to be designed such that we get to the bottom of the system and slowly decay. Okay, whoops. Gradient clipping operation looks a little like this. I don't have a slide for it because I wasn't able to modify it because it's a PDF, but gradient clipping effectively says that if we have the sigmoid operation, right, and we come up through the operation space here, we say, if this is 1, 0, right, the saturation points are going to happen at the very apex of either end of the system, but the gradients along this edge right here are going to be very, very sharp. So what do? We say, if the gradient is very high, we're going to plot the gradient characteristic. It's going to sort of start off with a low bound set point, and then the grad value is going to go up to a certain limit, right? What would continue to happen as we keep going into that space? Steeper, 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 steeper value, right? It's going to keep getting to be more and more. But instead what we're actually going to do is we're going to set a clip point. We're going to say past this point, that is the effective max, all right? That's the max amount of steepness that you can attempt to integrate for the gradient descent update process. LSTMs super need this because they reinforce themselves by sending previous output information to next sequence output information. They can also have very high-end epochtic learning, right? Grokking, as we talked about beforehand. They can train for quite a while, and then all of a sudden they'll come across a relationship to something that if they make the right connections, right? It's effectively the aha moment that sometimes I see students have, all right? That's one of the things that instructors live for, is to see somebody actually understand what they're talking about. Okay, it doesn't happen for me very often, but it's a little self-deprecating. Just a joke, just a joke. I think you guys are learning things. Okay, but no, in truth, that's actually kind of, I don't know if you guys have felt this feeling. Okay, you're watching your network learn. It's like watching a child take its first steps. You're like, oh, it's doing so good. It's so awesome. I'm excited. It's learning, right? This can be exciting when we find this thing where it's had an aha moment. It goes, oh, what if I have this and I have this thing? Crazy, they're like linked together. It goes, all of a sudden, error, right? Yeah. Adjust together. These things are linked, right? Like that's just the universe makes sense now moment, right? So what's going to happen? It's going to go, I'm going that way a ton, and it just overshoots the gradient, okay? It overshoots that place where it could have learned something, right? It overemphasizes that thing that it thinks it's learned, and by overemphasizing it, it actually overshoots the capacity that it would have in order to optimally find the gradient space. That is because, as I said beforehand, the potential additive capacity where something could seem to be increasing in significance over and over and over and over again until it becomes kind of the only thing the system can look at. So what we're going to do is we're going to tame the system down by saying, okay, always make sure that the value that's relatively present in that side memory characteristic is kept in check and can always effectively be negated when necessary by a value that could remove it, right? Could cause it to be forgotten if it's unnecessary in the future. Okay, we'll talk about transformers next. I will post up those videos for you guys, and I do encourage you to look through them. I think he does such an exceptional job of both describing the internal process as well as visualizing it. I will probably actually even be borrowing some imagery from those videos. I've already started to steal some. So, but we'll talk about that. That'll be our last item. And if you have any questions about the assignment, please, if you could come real quick and talk to me now, and I'll see if I can resolve this for you, okay? Otherwise, we're gonna be on Zoom, we're gonna have some hours on Zoom, both myself and my TAs, all right? And we're gonna be able to assist you with those assignments if you need to talk to somebody even after classes are over, okay? So now during the week, ask me, set up a time, come by, talk. But if it's during finals week, we're gonna still have some time where we can assist with that process. So good luck to you. I'll talk to you soon. Clarify for me. I don't know what the last